Hi, this is Dr. Dan here, and we're going to be going through practice problems involving solution stoichiometry and acid-base chemistry. So we're going to go through some of the different types of practice problems that you might encounter when you come across solution stoichiometry, especially involving acids and bases. There's some keywords that you might see for these kinds of problems, including neutralization, titration, solution making, stoichiometry, or pH, pOH. There are a lot of little buzzwords that we are going to be seeing when you are dealing with these, so look out for them. You might have to solve for pH, pOH, so we're going to go through two practice problems in this video. Please feel free to like and subscribe for more of these videos in the future, and let's go into our example. All right, so our first example is the following neutralization problem. So the way that this is worded is typically it gives you volumes that are being mixed together, and it might use that buzzword neutralize, or titration is what you're looking for, or mixing solutions is another way that this might be shown. So what this says is what volume, and it says in milliliters, of 0.450 molar nitric acid is required to neutralize 27.2 milliliters of 0.245 molar barium hydroxide. So let's kind of highlight all the key things here. So we have a concentration, and that's for nitric acid. We also have it has to neutralize 27.2 milliliters of barium hydroxide. So these are our key things. So let's go through the steps. The first thing that we always have to do for any of these types of problems is when we're given names, we have to write out the chemical reaction. We need to know how many moles are there going to be in this problem. So this is one of the things we are always looking for. So the first thing what we had was nitric acid, and that said it was neutralizing or reacting with barium hydroxide. So it's an acid-base reaction, right? Nitric acid is an acid, barium hydroxide is a base. So with this, what kind of reaction is it? So if you don't remember reactions, go to my types of chemical reactions video. That will help you with that part. But the whole idea here is that this is all about outside and inside are combining together. Being that this is a double replacement reaction, we could label everything CAB plus CD. We're labeling cations and anions with our letters to help us see that. Now with this, right, the first one, so outside is it's showing that we'll have water. So it's going to be H and OH combined. Whenever you have a hydroxide polyatomic, a little tip is write it as HOH until we have it balanced, because polyatomics are easier to balance when they're written in this format. Now, what's the other one? The other one is barium hydroxide. So we have, or sorry, not barium hydroxide, barium nitrate is going to combine together as well. So it's Ba. Now we always swap, drop, and check charges. So it's a 2+ on barium, 1- on nitrate. So when we are doing that, we got to swap, drop everything. Same with H and OH. They're plus and minus one, so they're already balanced. So we balance that. We do our swap, drop. Now the thing is, we have to make sure all of our atoms balanced. Now the key is here with balancing atoms is you want to try to check by starting with the polyatomics. So what do I mean by that? If we look, let's say with nitrate first, well, on the right-hand side of the problem, I have 2 nitrates. If I look on the other side of the problem a little bit farther away, we'll see that on the left side, there's only 1 nitrate. So if I go from 2 to 1, what's the easiest way to balance that is by putting a 2 out in front of nitrate. Now, this method is what I refer to as a zigzag method. So being that we have 2 nitrates, we'll look at hydrogen. So there's 2 on the left. How many do I have on the right? Well, being that we separated H and OH for a reason here to help us balance. So in order to do that, we'll have 2 hydrogens to balance the left and the right. We'll then zigzag to our OH, and we'll look, we have 2 hydroxides on the right, and we also have 2 on the right, on the left. So this is a balanced chemical reaction. All right. So now that we have that, what is our next step? So our next step in the problem is to list out all the variables from the problem. Now, why is that important? Well, the reason behind this, it helps us be organized and to see what exactly are we being given. So in this problem, the first thing that we have is that we have 0.45 molar of HNO3. And then we were also given what the concentration and volume was of barium hydroxide. So we have 0.245 molar of barium hydroxide, and it has a volume of 27.2 milliliters. So why do we do this is because it helps tell you where to start the problem. Our next step is to do stoichiometry. When it comes down to doing solution stoichiometry, we need to be able to map out our pathway here. And when it comes to solutions, the idea is that we need to start with a volume of one ingredient and convert it to moles. Moles are always the goal. So how do we do that? Well, the only way to really be able to bridge from volume to moles is by using molarity, right? Molarity is a conversion term that is very useful to us. So that is bridged by molarity of, in this case, molarity of A to get the moles of A. So what that tells you is the only place that you can start is with a chemical that has both the molarity and the volume. You need both things to start. Both molarity, volume, and molarity is where you start. So when we do that, we can then convert it to moles of B, which we can then convert to volume of B using the other molarity. So typically you're given one, maybe potentially two concentrations here. So we'll use the other molarity to do that, which was our HNO3. So the thing we're going to start with is barium hydroxide. So that is where we will start. So why don't we copy our information from up here. So we'll have our chemical equation with us and then our variables. All right. So let's bring that down. All right. So we have our problem here. What we're going to do is we're going to set up a stoichiometry process for ourselves. So we'll first have our volume is what we said we would start with. So we'll have 27.2 milliliters. Now our goal is to convert that to moles. So what is molarity? Let's take a look. Molarity is moles over liters. So if I have my barium hydroxide, that is saying that we have 0.245 moles over liters. Now, is there another way that this can be represented to make this a little easier? Well, there is. So if you think about being that this problem has to be in milliliters, how many milliliters are in a liter? Well, you might remember 1,000 milliliters is 1 liter. So we can actually represent this two ways. We can either say 0.245 moles is over 1,000 milliliters or over 1 liter. It's a shortcut. So it's always good to have those little shortcuts for ourselves. So let's plug that in. So if we have that 0.245 moles of barium hydroxide, and that's over 1,000 milliliters. Now, why is that important? Is the mLs. Now cancel the mLs. They're gone. And all we have is moles of barium hydroxide, which was our first step. Now, why did we have to balance the chemical equation earlier? Well, that was so that we can know the mole to mole ratio. So our next step is that we'll have 1 mole of barium hydroxide, and that's equivalent to 2 moles of nitric acid based on our chemical equation. So that cancels moles of barium hydroxide. That goes away. Now we have to convert it to volume, and we'll do the same trick with the molarity of nitric acid, which is 0.450 moles over 1 liter. or over 1,000 milliliters, being that our final answer has to be in milliliters. So let's plug that in. So we need to set it up so units cancel. They have to be opposites. And this is going to give us our final volume. And if you have to put it in liters for you, maybe for your homework that you have for your class, then you can leave it in over 1 liter if that helps you as well. You have either option, but you can see all those units are canceling out as we go through this process. And let's pick a different color here just so it can help illustrate the differences here of all these things canceling. All right, now when we solve, what are we doing? We're multiplying everything on top, dividing what's on bottom. So we have 27.2 milliliters times 0.245 moles times 2 moles times 1,000. We'll then divide that by 1,000, divide that by 0.450. And what we are going to get is 29.62 milliliters of nitric acid is required to neutralize this. Now we want to make sure we put in the right sig figs. So this is going to be 29.6 mLs is going to be our final answer of nitric acid. And that is how we do this style of problem. So let's go into the next one. So if I had the following example, which says calculate the pH of a strong base solution if you use 0.5 grams of calcium hydroxide to make a total of 2.5 liters of solution, what is the pH? So how do we use a pH equation? Well, one of the big things about any of those is that it comes down to identifying, is this an acid or is this a base? So the ingredient that we were given in the very beginning was calcium hydroxide, which if you remember, anything that has a hydroxide in it is a base. So this one is going to be, we can only solve for pOH first. So let's write how this is going to dissociate because we want to know how much hydroxide there is in solution. So if this breaks apart, we have 1 calcium ion and 2 hydroxide ions that are in solution, right? So both of these are in their aqueous state and they are dissolving. Well, now why is that important? Well, we were only given how many grams of calcium hydroxide. We have to convert that to moles of hydroxide. Why moles? Well, remember our formula is pOH is equal to the negative log of the concentration of OH minus, meaning that OH minus has to be in molarity. So we have to go from moles and then divide it by the liters that are in solution. So we have to use a few different pieces of information that are here, right? We have the 2.5 liters and the 0.5 grams that are here. So let's first calculate moles. Let's go from 0.5 grams of calcium hydroxide to moles of hydroxide. So when we are doing that, we're going to map out our reaction, right? So we're going to go from grams to moles, and that's for calcium hydroxide. And then we are going to go to moles again using that 1 mole of calcium is equivalent to 2 moles to 2 moles of hydroxide. Okay, so map out your process. It makes it a little bit easier when you're trying to figure out exactly what is it that you are trying to work on in your problem. So with that, we will determine the concentration. So we started with 0.5 grams of calcium hydroxide. We need to multiply that by the molar mass. So the molar mass, when you look up and calculate those values, it's 73.968 grams of calcium hydroxide per mole of calcium hydroxide. So when we do that, we'll see that grams cancels grams. And now the next step is we have to do the mole to mole equation, which as we saw earlier is that 1 mole of calcium hydroxide dissociated into 2 moles of hydroxide. So now when we do that, we can see that, all right, the moles cancel and it gives us how much hydroxide is in there. Now remember, this is not what the molarity is. This is only how many moles there are. So when we solve that, we'll have 0.0135 moles of hydroxide. Now, how do you find a concentration? Well, this is where we have to treat molarity like a formula, right? Molarity is moles over liters. So we're going to plug in our moles and our liters. So we'll put moles on top, and then we'll divide it by how many liters of solution are, which were 2.5 liters of solution. Now, when we do that, we will get our final molarity, which is 5.4 times 10 to the negative 3 molar of hydroxide. Okay, so that's the OH minus concentration, and that's our important value there, right? So that's what that is telling us. Now, let's actually go and solve what our equation was. So we just had to set it up there. The first thing with pOH, right, is that we take the pOH of the negative log of OH minus. So we are going to plug in our number into this equation. So we'll have the negative log of 5.4 times 10 to the negative 3 molar. And what that's going to give us is a pOH of 2.27 as our value. Now, are we finished? Well, let's check the original problem. So if we scroll up here for a second and we go, it says, what is the pH? So what's our last step? Well, if you remember, there's a bridge between pH and pOH. So with this is that pH and pOH, when you add them together, is equal to 14. So what we have to do is subtract the pOH from the 14 value. So 14 minus 2.27 is going to equal the pH, being that is being plugged in here. So when we do that, it's going to tell us that our pH is 11.73, which when we see that, that is extremely basic from our values that we have. Thank you so much for watching this video. I hope that this helped with your general chemistry needs. If you need anything else for different practice problems, feel free to like and comment down below so that way I can help you with future content. Please subscribe for more videos, more practice problems, and how-to tutorials are to come to help you pass your chemistry class. I'll see you all later. Bye now.